Alright everyone, welcome back to Linear Algebra. Welcome back to Linear Algebra done well by Sheldon Axler, and let's continue this. So last time we left off in question 17 where I got really stuck for a long time, and I'm not gonna lie, this question took me a very long time, and I even took a peek at the answer, but so there's this person who posted a comprehensive answer to these linear algebra done right sections by Sheldon Axler. I think they have a GitHub repository for it, but otherwise it's only posted for the odd questions, and this question just happens to be odd. I looked at it. I had a similar beginning to their solution, but they were doing more like a matrix form stuff, and I was more thinking about it in terms of linear transformations. So I'm going to show my method as well. Let's begin. So the premise is that you have S, so first you have a vector space, and then you have the set of all operators over that vector space, and then you have a subspace of the set of all operators, where supposedly epsilon is a subspace, and the subspace satisfies some properties where if you take any element from the subspace and any element from the actual set, then composing them either way will land you back into the subspace. So here's one way to think about this interesting question, right? Consider constructing a basis for this set of all operators. So if you consider constructing a basis, then what you end up with is, well, these little function looking things. Let's say V is n dimensions, right? I think it's finite. Let me check actually. Yeah, it's finite dimensional. And what these little guys do is for Eij, if you put Vi into it, you'll get Vj back. But if you put any other vector into it, if k is not equal to I, you'll get 0 back. And of course, like this Vi, Vj, like this kind of stuff comes from the standard basis, or if there's not a basis, you can easily identify one. There must exist one, right? You can construct one that lengths n. Well, not necessarily you have an algorithmic way of constructing one, just that one exists. So that you immediately know that epsilon have such a, or rather the set of all linear operators have such a basis, and that's the notation that I'll be using from now on. So consider the fact that what happens if you have, because this Q can be from any, it could be literally any operator in LV, so I get to choose exactly what it is, but this L I do not get to choose. So let's say we take some arbitrary map in L, and then let's compose L with Q on V1. And first I set Q to be epsilon 1, 1. So that means Q of V1 is equal to V1, and Q of V everything else is equal to 0, where J is not equal to 1. And then, so let's say that this is equal to L of V1. That's, there's not much going on here, I don't think. So L of V1 is going to be equal to some C0 V, well, I don't have zeros here, C1 V1, up until C and Vn. But all the other part goes away, right? Because Q maps this to be 0. This is the part that matters. Q of C1 V1 is going to be, let's say, C1 times Q of V1. And what that's going to be is just C1 of C1 times V1. So you notice something interesting here, which is that because, let's say because L composed with Q, because L composed with Q must be an epsilon, the fact is that epsilon contains some multiple of epsilon 1 1, right? Because this is exactly what epsilon 1 1 is. If you give it epsilon, if you give it v1, it spits out some multiple of v1. And the thing is, you can trick the epsilon subspace into accepting basically every such combination, whatever combination you want. You can trick the subspace. You can force it into accepting such combinations. So let's say you set you say q is equal to epsilon ij. Then q of L of vi, let's say this is equal to some, I don't know, some, once again, C1 U1 Ci Vi, then through Cn Vn, right? The rest doesn't matter, it's trunk. Like, what matters is in the middle. And you get Ci times Q Vj. Sorry, hold on. Ci times Vj. So once again, Q composes L as an epsilon. Epsilon contains multiple of epsilon ij. So in fact, that you can notice that epsilon is actually spanned by epsilon. Epsilon contains all linear maps, or actually all basis elements. It contains all basis elements of the set of linear operators, which means that in fact they are equal. Or there's one thing we could have also said, is that if epsilon only has zero map, the zero composes Q is also zero, so that's always fine. So of course I forgot to mention that assume that L is some non-zero map in epsilon. That's what you want to assume, because the zero case is not too hard to show. So we don't really, you can sort of hand wavy and say that that's what it is. Alright, let's go to question 18. So we have V and the linear map, the set of all linear maps from F to V. We want to show those two are isomorphic. So first, what you probably want to do is you want to probably construct a isomorphism, because it doesn't specify V is finite dimensional. So speculating on the dimensions of these things is kind of pointless. But in fact, if they were finite dimensional, this question would probably be already over. So for arbitrary V in the vector space V, what you want to do is specify a function t from V to L f V, such that t of V is equal to, such that t of V of C, where C is in F, results in V. This is your specification, right? This is precisely what you want to define. In a less scrupulous manner, you perhaps could say t of V is defined as G, where G of C is equal, that's my mistake, should have been a C. So where G of C is, G of 1 is equal to V. And because the way you think about it is, since you are mapping to one dimension, the transformation of one of your vectors, or I guess the transformation of one is enough to determine what your entire linear transformation is destined to be. So all you need to know is what G of 1 is, because then G of C is just C times G of 1, which is going to be CV. So it's uniquely determined. This definition is clear enough on its own, and if you want to be really pedantic about it, you can first show that it's a linear map, which I'm just kind of annoyed to show, because it's just it's quite silly. There's not a lot of purpose to it. But I mean, you can most certainly do this. I don't see why not. It's for all C and F, and V and V. So first you got the additive property And then on top of that, you have homogeneity, which you need to show for linear maps. So if you want to show linear maps, what you could do is have lambda here. This is going to lead you to, let's say, hold on, lambda CV, yeah, this is not tricky actually, lambda times CV, and then pull the lambda out, and then you get TV composed with C, and then you're done. Right, this shows homogeneity. And then, so you have your linear map, and then what you want to show next is that the linear map T is surjective and injective at the same time. So I don't think that should be difficult, because if you want to consider this, you want to first show that the kernel is just the empty set. So TV of C is equal to 0 for all C. Then, in fact, you know for a fact that TV of 1 must be equal to 0, because TV of C is just equal to C times TV of 1, which is equal to C times 0, right? That's what you probably want to know. Actually, I don't need to do it this way. I can show it without using the kernel, because I feel that it's actually probably much more convenient in a way for all C and F. Then what you know is that let's say equals to W, right? So yeah, this is not too bad to show. In fact, you don't need all of the C's, you need one C, so you're good. So for arbitrary, so then we want to show surjectivity. So arbitrary linear map, let's say phi, which is present in this. So then we want to find what phi of 1 is, and let phi of 1 equals to D, then I think all there is left to do, okay, sorry, I mean V1, I guess. Then all there is left to do is let TV1 is equal to phi, then it's surjective. And we're done, right? Because the reason why it's equal to phi is because for each C, in the field, TV1 composed with C will be equal to phi of C. But perhaps you can first write that this is equal to CV1, and then this is equal to C phi of 1, and then this is equal to phi of C. Then these two functions, TUV1 and phi, agree on every single input, therefore they're the same function. So in fact, that you've produced this function and shown that T is surjective and injective, which means that it's an isomorphism. And then since it's an isomorphism, or sorry, actually I skipped a step, because it's injective and surjective, you know it's invertible. And since it's invertible, you know it's an isomorphism. And since it's a, no, actually, if it's isomorphism and it's a linear map, if it's invertible and it's a linear map, then it's an isomorphism. And since it's an isomorphism, you indeed show that these two spaces are isomorphic vector spaces. So there's not much in that, but you need to be familiar with how to construct these isomorphisms. I think that's all that's required to do this. Suppose T is a element of the set of all operators where you map polynomials to themselves. So you want to show T is injective. And so degree T, P, less than degree of P. Okay, sorry, give me a second. Every non-zero Okay, so when you look at this, actually when I looked at this, I think B looked a lot easier than A for some reason, because it looked very inductive. And A looked like it's something you can show once you show that B is true. So A to me immediately looked very strange, because we know for a fact that the space of all polynomials is not finite dimensional, which means, showing surjectivity is going to be very difficult. Because if it was finite dimensional and you have an injectivity from an operator, then you know it's surjective immediately. But I lose out on a lot just because the polynomial space is infinite dimensional. So in fact, you can't know anything about this. So what you are forced to consider is perhaps, and I think there's probably a better way than the way in which I'm doing this, but I think the way you're forced to consider is to actually do question or sub-question part B first and then go back to question A. Because if you consider this to be true, then surjectivity will be easier to show. Right? Not necessarily a lot easier, but just a little bit. So, yeah. So consider this to be sort of an inductive case. So induct on degree of polynomial. So what you want to do is induct on the degree of the polynomial starting with the degree 0, which is the base case. So if a polynomial has degree 0, then, transformation of a constant. So it's gotta be, so this result, let's say, let's call it Q. Q has degree 0 or less than 0. But if degree of Q is less than 0, then Q is forced to be 0. Then kernel of T is not equal to 0, because then 1 is an element of it. So in fact, we know that Q has to have degree 0. And if Q has to have degree 0, then it's very clear that the degree of the transformation of P is equal to P is shown for the base case. And then we will do this for the recursive case. Now consider that P has degree n minus 1, or no, sorry, what I want to say is degree transformation of the polynomial is equal to the degree of the polynomial for all polynomial with degree less than or equal to n minus 1. And we want to show that degree of transformation of P is equal to the degree of P when degree of P is equal to n. This is quite a strong condition, but if you were to consider that the transformation of P to be Q, for example, where Q has degree, or degree of Q is less than n, then what you must notice is that the degree of Q is spanned by, okay, and I need to find more space to write this out. So the degree of Q is in fact spanned by transformation of 1, transformation of x, and so on, all the way up to and not including x to the n minus 1, right? Because, and this is a very bold claim, but I am definitely able to claim this because this has degree 0, this has degree 1, etc. This has degree n minus 1. So in fact, this spans the entirety of the polynomial space of degree n minus, I don't know if that's how you call it, the polynomial space of degree n minus 1. or perhaps the better way to say is a polynomial space with dimension n. But so degree q, whatever it is, like q must be in this space because q has degree less than n. So in fact, it must be in the polynomial space of dimension less than n. Or sorry, it must be in this, whatever it's called. So that's a problem because q is injective, or sorry, that's because t is injective, right? If you can find a linear combination c1, t1, etc. through cn minus 1, txv and minus 1 such that they equal to q, then that's a problem because this is equal to cn t of x to the n. And that's not okay because what you could do is this linear transformation is just stick all of the linear combination components inside, and then this becomes another a minus 1 degree polynomial, and then these guys are equal but not the same because this guy has degree n minus 1, this guy has degree n. So you clearly should not be allowed to do this because this breaks the injectivity, which means that transformation over x to the n should just be another, or let's say polynomial of degree p should be another polynomial of degree p, right? So this b is apparently not terrible to show. Like, it looks deceptively more difficult than a, but it's not. And once you show it, then a becomes possible. It's not easy to show by any stretch of the imagination, but it becomes possible, right? So consider you have some q, some arbitrary q, we don't know, in the set of all polynomials. And since we have fixed such q, we know let this polynomial have degree n, or let it be m for this time, because why the heck not? And then you know for a fact that because this polynomial has degree m, if you take t of 1, t of x, all the way up to t of x to the m, let's say you put all these together and you span them, these guys should span the polynomial space of m plus 1. No, just m. Oh, geez. Okay, yeah, it should just be m. Yeah, it should span polynomial space of m degree m, and then this will be in that space. Then you can do that linear combination trick again, so I won't do it, but you know what I'm going to say. So it's not too difficult. Well, like, it's difficult in the sense that once you realize it's not difficult, it's not difficult. So it's stupid like that. But like, most of math is like that. Like, the things you think about for 2 days or 3 days, and one day you realize you can think for 10 minutes and immediately understand it, is a pretty strange behavior. It just shows you how crazy the human brain is doing all that background calculations while you're resting or doing whatever. It just thinks about all this. Because you certainly didn't make that gap while you were actively thinking, most of the time at least. Sometimes you contribute towards the result, but most of the time it's the passive thinking. So you gotta credit your brain for being very good at multitasking, you know, and it's a credit to human evolution that we were able to get to such a stage. Anyways, so we want to prove that the following are equivalent, so the way I'm going to write this is that I'm going to write this as a matrix because I don't see why not. I'm too lazy to write this as anything else, and in fact I don't think that this problem is harmed by writing it as a matrix. So consider this, right? This then becomes a linear transformation. So let's say this is the matrix representation of a linear transformation. The transformation goes from the space of n plus 1 to n plus 1. Actually, if I do that, then I probably don't even need to write all such fancy notation. I can just say A is a matrix going from a row vector to another, or sorry, a column vector to another column vector, right? And the top, this part, this thing is saying the same thing as well. The kernel of this matrix is the zero vector, and the zero vector only. So since that it's this, that means that the matrix A is injective. Or at least the linear representation the linear transformation represented by the matrix is injective. Since it's injective, then it must be surjective as well. And this is not immediately clear because you're not quite operating over, or are you operating over the same field? I mean, yeah, A is a linear, A is an operator where the space it's operating over is the column vector space of degree n, or whatever you want to call it. So injective does imply surjective, but if you're not convinced, that's certainly what I was thinking, because I was not too convinced by something like this. Then you can write out that this is true. Dimension of kernel is 0. The dimension of the input space is n, so that means the dimension of the range is n, and the range of A is in the space of dimension n. So certainly these two must be equal, which means it's surjective as well. So, and this is exactly what surjectivity means for each C1 through Cn. So for each member of there exists an element in here which you get the point, like, yeah. So yeah, okay, did I write this the other way around? See, that's stupid, but like the crazy thing is that didn't affect how this problem would turn out, because it had nothing to do with the problem. The way I wrote the matrix is not key to the understanding of this problem. So okay, so that is all the questions from section 3D. So finally, after many days of being stuck and not progressing at all, I finally moved past this. Alright, let's go to section 3E. Okay. You know what, actually I think I might upload this first, because this does end the section and I want to start a new video with a new section, so I'll start that off later.